Hello everyone and welcome. So in this video we'll be discussing about the simple linear regression, which is a part of supervised machine learning algorithm. And if you don't know what is a supervised machine learning, then let's have a quick intro. So supervised machine learning algorithm is one of the many algorithms that machine learning has, like the unsupervised learning or reinforcement learning or live training. So depending upon the use cases, we have different machine learning algorithms. And if you are a beginner and you don't know what is a machine learning, so in a nutshell, machine learning is a subset of artificial intelligence in which there is a model which is nothing but a mathematical algorithm, and using the algorithm we create a model which learns from, as the name suggests, machine learning. So the machine learns from historical data, and when we present a new data to the model, so based on the historical learning, the model predicts a new outcome or some new values. So we'll come back to this example. So as you can see, there is a machine learning model, and inside which we are feeding a data. The data is like these might be the features or attributes, and we are also assigning the labels to it. So in supervised machine learning algorithm, the training data you feed is always associated with an desired solution. Like these are the apples, so the model will know like this feature, this color, this figure will refer to an apple. And after the model is trained, when we'll be feeding with a new variable, which is an apple, the model will be able to tell like it is an apple. So this is the whole concept behind the machine learning. Like we have a model which is trained on some historical data, and when we provide some new input based on the historical learning, the model is able to predict an outcome. So this is a classification problem where we have the outcome is an whole, like apple or oranges. And in simple linear regression, we don't have labels, we have the values. So the regression problem is related to making predictions about the real world quantities. In real world cases, like we'll be having many features as an input, but in simple linear regression we have only one variable as an input. As you can see, like this is a single variable. So we have one independent variable. It is known by different names, like somewhere it is called response variable, somewhere it is called dependent variable, somewhere it is known as target variables. Similarly, the x is an independent variable, and it is also known as attribute or feature or predictor variable. So the whole concept is behind how much with the different values of x, how much y will be changing, and the different use cases. There are various examples by which you can understand how the simple linear regression works. Like how does the sales volume changes when there is a change in price. The price might be x and the y will be represented by sales. Then how the sales volume is affected by weather, or how many customers can you expect today. So there are various examples. So let's say you want to predict the variation in sales by different advertisement. In this case we are dealing with a simple linear regression, so there might be different advertisement channels. Like you might be doing some advertisements via newspaper, via TVs and via radios. So how much each is contributing towards the total volume of the sale. So the basic idea behind that is same. Once we are clear with the simple linear regression with single variable, then the multiple linear regression also follows the same course. So all these questions have a common structure. They ask for a response that can be expressed as a combination of one or more independent variables, which are also known as covariate or predictor variable, and the process involves the transition from data to model. So the whole algorithm revolves around this equation, and each model is solely determined by its weights and biases. And weights and biases are nothing but the terms that we use in machine learning. Weight is simply the slope of the line, and biases is the constant variable. And biases, why it is called biases, like let's say for an example, like you want to predict the salary change with the experience. So whenever a fresher joins a particular company, he has a fixed salary, and based on the number of experience, the salary goes on increasing. So whether or not he has experience, and there will be some fixed amount at the time of joining when he joins as a fresher. So that fixed amount is known as a bias in that particular example. Let's say for another example, if you pay the electricity bill for your house, whether or not you consume electricity, there are always some fixed charges that you have to pay, and then the amount you pay is the number of electricity units you consume. So independent of how many electricity units you consume, there are always some fixed charges that you have to pay. So those are known as the biases. And the weight shifts the mean of the response variable. So let's say you have a slope of 5 units, so with 1 unit change in the predictor variable, you will be having a 5 unit shift in the mean of the response variable. So the weights and biases are the main parameters that define how well our model is able to predict the thing. That is why we are more interested in finding the accurate values of this B1 and B0. And we do the random hit and trial method to find this B0 and B1, which is able to predict the response variable. And there are various ways. There are 3 ways basically. Like if you keep the bias constant B0, then you have this make this line as a pivot, and then you can rotate this, so B1 will be varying. And then if you keep the slope constant, and then so that will be a rotary motion in the first case. Then in second case you can keep the slope constant and then vary the biases, so that will be the translational motion. And in the third case you can vary both. So there are a lot of parameters and the value can be infinite. We have to find some ways by which we can reduce this, by which we can find the values of B0 and B1. And once you have found the weights and biases, then the forecasting of the new values becomes quite easy. You just have to put the new parameters in the equation and you will be getting a response. So varying the B0 and B1 can goes up to infinity. Like we have to run every outcome, which is not possible. So how do we assume like which values are the best? So for that we have different objective functions. An objective function is nothing but a measure of how well our model's output match the targets. So our main objective is to plot all the values of y hat, which is the values predicted by our model, and then find the error against the original labels that we provide as an input. And the main aim is to reduce this error. So the method of minimizing the sum of squared residuals in terms of least squares is known as ordinary least squares, or OLS. In single variable you will be having a line, and in 2 variables you will get a plane, and in 3 variables you will be getting a surface, so the thing goes on. So then in ideal condition the actual values will be on the predicted line. In that case our error will be 0. So this is nothing but a minimization problem. So we'll take it as a function of y equals to fx, so which is fx is the error function, and derivative is equals to 0. So this is a minimization problem, and when we'll be equating this derivation to 0, and if the derivative is positive, then we are on the right side of the parabola, and if the derivative is negative, then we are on the left side of the parabola. And when the derivative is equals to 0, then we are at the bottom, and this is a global minimum of the cost function. So let's quickly get through an example to understand this using the mathematical implementation. So here we take an example of prediction of monthly salary of different employees with different years of experience. So this monthly salary is a thing that we want to predict with number of experience a person has. So this will be the label as an input, and these are the predictor variables. So x will be the experience in years, and y hat is the years monthly salary that we have to predict. So y will be the target variable. From the previous cost function we have this error that we have to reduce to 0. So we'll simply put all these values in the equation. Y minus y hat to the power 2, and y is simply the label, like 3.9, 4.6, 3.8, 4.4, 3.9, 4.6, 3.8, 4.4, and then 4. And y hat is equals to b0 plus b1x. So we'll simply put all these values, and x will be the input variables. So there are 2 variables, b0 and b1. So first we'll take the partial derivative with respect to b1 and another with respect to b0, and from doing this we'll be having 2 equations, and when we'll be solving these equations then we'll be getting the values of b0 and b1, and we have to simply put these values inside this equation. Then we can give input of the predictor variable, and then we can have our y hat. So that's how simple linear regression works. So in the next part we'll see how we can implement this machine learning algorithm of simple linear regression using the ordinary least squares using Python and scikit-learn. Alright, so in the last part we implemented simple linear regression using the calculus. So now we'll try to replicate the same using the Python, and for that I will simply open my Jupyter notebook. So to begin with we need to first import the required libraries for performing this linear regression, and I will be using sklearn module. So from sklearn import linear regression, and since it is a model, so it will be like linear, hit tab, it will be linear model. Then for creating the data frame, I'll be using pandas, so import pandas as pd. Since we have to compare the mathematical approach and how the sklearn performs using Python, so I'll be using the same data that we did in the calculus part. So I have saved this using with the name of slr in the same directory. So I'll simply load this as a data frame. So df is equals to pd dot read csv, and sl hit tab, it will automatically detect the csv present in the current directory of the i/nb file. So just to check it, simply say df. So this is the data frame. So now I'll create an instance of our linear model. So I'll say lr, I'll simply say model is equals to linear model dot, then I have to implement linear regression, and for the x part I'll be simply saying like f, then I'll be doing the slicing. So df dot ilog, and for this like I'll have to say like all rows, then all columns except the last one dot values. We don't have to take the headers, the column header and the index. And similarly for y, I'll simply copy this, and we have to just replace, like we have to take all rows and we have to take only the last column. Oh, sorry, this is not a function. Now if you see, you have an x of all these values. So since this is a simple linear regression, we are only having a single feature, but this template works in very well when you have multiple features. So the provided you have the label or the target variable as a last column, so it will automatically detect all the rows, only the last column as y, which is usually the template for the target and labels, and x will be automatically taken as all the features except the last column. So this is a good template. Like there are several other ways also, like we usually do df, then we do df.drop, and we simply from all the data frame we just drop the column that is the label, but in that we have to type manually the name of the last column. Like here it is salary, so we have to type df.drop, then within the commas we have to say salary. But within the by using this template you don't have to type anything, it works in all the cases. So now we have got the values. Now we have to simply fit into the model dot fit, then begin with x, then y. So the model is fitted. Now we have to simply just do like model dot hit tab, then you'll see all the things that are available, and we have to say intercept. So we get like 4.07281, and if we match it with our original one, then we have 4.07281. so we got the b naught, exact the same value. Now if we try with for finding model dot coefficient, then we get 0.0414, which is the same. So this is how you can implement linear regression using Python. Now if you want to predict for some new values what will be the salary for particular set of years of experience, so you have to simply say model dot predict, and remember since it is an array, so you have to provide values in double arrays. So let's say I want to predict for 4.5 years of experience, so I'll be getting around 4.25, whatever the unit of the salary is. So if it is 8.5, it is 4.2. So this won't be accurate since our data is very less, and it is always a good practice so to predict the values which is within the range of the values that you are giving as an input. So here we are giving the range of the, since it is a model, so this is a drawback of linear regression. Like whatever values will be giving as for predicting, it will be giving some result, but that won't be accurate. So this thing you have to take care manually, like whatever the range you are providing as an input, because the model is trained on that particular set of range, like it is from 1.1 to 2.2. so anything beyond 2.3, it will be somewhat little accurate or close to the value, but that won't be a correct estimation. So the best practice is always to predict any value that is within the range of the training data. So in real case, you don't have like 4 to 5 values. This I did intentionally just for this calculation part, because this more than 10 or to 15 variables or the hundreds and thousands, it won't be possible for me to do the mathematical calculation. In real world, you have like thousands and millions of data. So this model helps in then predicting all those things quickly. So if you have found this video useful, give it a thumbs up, do subscribe and share with your friends. And if you have any queries or suggestions, please drop down in the comment section. Thanks for watching, and I hope to see you in my next video.